The topic is magnetic force. What is magnetic force? A force due to magnetic field vector B is called magnetic force. That magnetic field should be a steady magnetic field. Now there are three ways in which we get a magnetic force. The first is when a charge is moving in magnetic field B vector. And the second is on a current element that is situated in external magnetic field B, and third is between two current elements. So there are three ways in which we produce a magnetic force in the external magnetic field B vector. Now the first is a force on a charged particle. As we know that in case of electrostatics, when we place a charged particle Q in a electric field E, there is a force and whose direction is along the electric field intensity E. Here the positive charge is placed in the electric field, external electric field. It is set free or moving, then the charge plus Q is accelerated in the direction of E. That is due to the electric force F suffix E. And due to that force, there is some work. So, as a charged particle Q is placed in external electric field, it is moved along the electric field E. But when a charged particle is placed in a magnetic field B vector, then nothing's happened. It remains at rest. There is no work because there is no magnetic force when a charge is set free or rest in the magnetic field B vector. So this is the difference. When a charge is placed in the electric field, there is a work done, but when a charge is placed in magnetic field, there is no work done. But when a charge is moving with some velocity in the external magnetic field B, then there is a magnetic force, and the direction of this magnetic force is always right angle to its velocity v vector. So the magnetic force is only when the charge is moving with some velocity in the external magnetic field B. If a charge is set free or at rest in the external magnetic field, then there is no magnetic force. But when a charge is moving with some velocity in the external magnetic field, then only there is a magnetic force, and the direction of the magnetic force is right angle to the velocity of charge. The direction of the magnetic force gives the acceleration vector, while the direction of the velocity gives the velocity vector. So the direction of the magnetic force is always 90 degree with the velocity vector. Now the formula of magnetic force is obtained by using a cross product, by using right hand thumb rule. In this we take a cross product of velocity vector and B vector, that is V cross B vector. So the direction of the magnetic force is towards acceleration vector, that is normal to the plane in which we take a cross product V cross B vector. So the magnetic force is equals to product Q into V cross B vector. So this is the formula of magnetic force, that is Q V cross B vector. Now in magnitude form, the magnetic force Fm is equals to Q magnitude of V vector into magnitude of B vector and sine theta. Theta is the angle between velocity vector V and magnetic field B vector. Now there is a case when a moving charge having both electric field and magnetic field, because the electric charge having a static electric field as well. So if there is a moving charge in both electric field E vector and magnetic field B vector, the total force is equals to summation of electric force and magnetic force. Electric force is equals to Q into E vector, while the magnetic force is equals to Q V cross B vector, and the direction of magnetic force is 90 degree to the direction of velocity vector. And there is a cross product of V cross B vector. So in this way we get a total force when a charge is moving in both electric and magnetic field, which is given as Q within bracket electric field E plus V cross B, and this is called a Lorentz force equation. The Lorentz force equation has application in electron orbit in magnetron, proton path in cyclotron, etc. So here we conclude that when a charge is placed in electric field, there is a work done. When a charge is placed in magnetic field, there is no work done. But when a charge is moving with some velocity in the external magnetic field, there is a magnetic force, and the direction of magnetic force is a acceleration vector, and it is always 90 degree to the direction of velocity vector. And the formula of magnetic force is Q V cross B. So this is the first way to get a magnetic force due to moving charge in the external magnetic field. The second way to get a magnetic force is on the current element placed on external magnetic field. Since we know that the magnetic force is equals to Q V cross B, and here we take a current element in the external field. So here we consider a conductor in which a steady current is flowing. This conductor is having a cross-sectional area as that of cylindrical system, and here we take a small differential length dl. From this differential length dl, we get a current element I into dl vector. This I into dl vector is analogous to a small charge, that is differential charge dq in case of electrostatics. So in case of magnetostatics, the current element is denoted by I into dl vector. Since as we know that small charge dq can be written in terms of volume charge density, that is dq equals to rho v into dv, and dv is the differential volume of this current element. The volume of this current element is dl into ds, where ds is the differential surface, that is a cross-sectional area of the conductor, and dl is the length. So the volume is ds into dl. So we put dv equals to ds into dl. Now we know that the differential current di equals to dq upon dt, that is charge upon time, rate of change of charge with respect to time. So we put the value of dq here. So di equals to rho v ds dl upon dt, and here the dl upon dt is a differential velocity dv, that is displacement upon time dv. Now from here we can get a current density J vector, that is a ratio of di upon ds, current upon area. So the current density J vector is equals to rho v into dV. And this is a current density for small differential volume. To get the total current density, we take a integration. So it get a J vector equals to I upon S, where S is the area of this conductor. And that is equals to rho V into V vector. So there is a relationship of current density and velocity vector in terms of volume charge density. That is J vector equals to rho V into V vector. So here we take a relationship of J vector and V vector. Now as we know that the current element in magnetostatics are determined in three ways. First is due to line, that is ideal vector. Second is due to shade, that is K vector into ds. And third is due to volume, that is J vector into dV. Here K vector is called surface current density and J vector is simply a current density. So here we take a formula, that is ideal vector is equals to J vector into dV. So in place of J vector we can write rho V into V vector. So ideal vector is equals to J vector into dV. That is rho V into V vector dV. And we know that rho V into dV is dq. So we write ideal vector equals to dq into V vector. So this is a elemental charge dq moving with velocity v, and this is equivalent to the conduction current element ideal. So in this way the conduction current element I into dl vector can transform into a elemental charge dq that is moving with velocity v vector, because we know that the charge is moving with some velocity, then only there is a magnetic force in the external magnetic field. Now here the current element ideal is get transformed into a elemental charge dq that is moving with some velocity v vector. Now we take a formula of magnetic force, that is q v cross b. Since this is the total magnetic force for a small elemental current, that is ideal vector, there is a small differential magnetic force that is denoted by d fm vector, which is equals to dq v cross b. Now in place of dq into v vector is equals to I dl vector. So the small differential magnetic force d fm vector is equals to I dl vector cross b vector. To get a total magnetic force we can integrate along a closed path, that is closed line integration I dl vector into b vector, because we know that the current is flowing in a closed path. That's why we take a closed line integration of I dl vector cross b vector. So in general we can write that magnetic force Fm vector is equals to I L cross b vector, where L is the length of the conductor, total length of the conductor. So there is a magnetic force due to a current element that is equals to I length vector into magnetic field B vector. Now in this we consider a magnetic field B vector, and in this magnetic field there is a current element, means there is a conductor in which a current is flowing, this conductor having a length L. So we take a cross product of L vector and B vector and we get a magnetic force F suffix m, and the direction of F suffix m is normal to the plane where we take a cross product L cross B, and that is the direction of magnetic force is obtained by using right hand rule. Here we take a cross product of L vector cross B vector, so we move L vector towards B vector, so we get a direction that is downward. So the magnetic force Fm vector is equals to I L cross B vector, and the formula of the cross product is magnitude of L vector into magnitude of B vector and sine theta. Theta is the angle between these two vectors. So the magnetic force in magnitude form is equals to BIL sine theta. We can also having a formula of magnetic force in terms of current element K vector into ds. So in place of I into dl vector, we can write K into ds vector because the current element is equal. They have same unit, that is ampere meter. So in place of IDL, we can write KDS, and we can also write J into dV. So the magnetic force Fm vector is equals to surface integration K vector ds cross B vector, and also magnetic force is equals to volume integration J vector dV cross B vector. So from here we can write as the magnetic field B vector is equals to force upon some current element. Here the current element is IDL vector or K vector into ds or J vector into dV. And the next third case is to determine the magnetic force, we take a two current element. So the topic is force between two current element. Here we consider a two conductors in which a two current is flowing. In a first conductor there is a current flowing I1 in a closed circuit, and in a second loop there is a current that is I2. So here we take a two current I1 and I2 flowing in a closed circuit. Due to this there are two current elements. In a first loop there is a current element which is called I1 into dl1 vector, and the current element in second loop is I2 dl2 vector. Now as the current is flowing in both the current elements, there is a force between these two current elements that is depend upon the direction of the currents. As the current I1 and I2 flowing in the same direction, there is a force of attraction, while if the current I1 and I2 flowing in opposite direction, there is a force of repulsion that is shown in figure. The conductor 1 carries a current I1, so around this conductor there is a magnetic field, and the direction of magnetic field is shown by dot and cross. Similarly, the current flowing in conductor 2 is I2, and its magnetic field is also shown as figure. So between these two conductors there is a opposite direction of magnetic field, so there is a force of attraction. But in case of current flowing in opposite direction, the magnetic field between these two conductors is of same sign, that is of same direction, so there is a force of repulsion. So in this way we get a magnetic force between two current elements that depend upon the direction of a current flow. Now we consider that B2 vector is the differential magnetic field for loop 2 by the current element I2 dl2. I2 dl2 is the current element of second loop. Due to this I2 into dl2, that is the current element, there is a small differential magnetic field. We call it B2 vector. Now we take a loop 1 Here we get a differential force dF1 on a current element I1 dL1, that is due to current element I1 dL1. So the force on current element I1 dL1 due to differential magnetic field dB2 is given by d within bracket dF1, because dF1 is the differential force on current element I1 dL1 due to differential magnetic field dB1, and the force on a current element I1 dL1 due to magnetic field in second element, that is differential magnetic field dB2, is given by the formula, that is differential dF1 vector is equals to I1 dL1 cross dB2, because the differential force dF equals to I dl cross B vector. So we use this formula, and the force on current element I1 dL1 due to dB2 is given by d dF1 equals to I1 dL1 cross dB2, because dF1 is the force, differential force on current element, and that is due to dB1, and the force on current element I1 dL1 due to dB2, that is the differential magnetic field in loop 2, is differential dF1. Now in place of dB2 we can write mu naught dH2. This is a relation of magnetic flux density and magnetic field density, B equals to mu H. So dB2 is equals to mu naught dH2. Now we using a Biot-Savart's law. According to Biot-Savart's law, the magnetic field intensity dH2 vector is equals to I2 dL2 vector cross unit vector R21 vector. The unit vector R21 vector is the vector between current elements I1 dL1 and I2 dL2. Here the direction is from loop 2 to 1, that is from current element I2 dL2 towards I1 dL1, because we have to determine the force, differential force on I1 dL1 due to differential magnetic field dB2. So here we use a Biot-Savart's law, that is dH2 equals to I2 dL2 vector cross unit vector R21 upon 4 pi R21 square. R21 is the magnitude of R21 vector. So after putting the value of dH2 in the above equation, we get a differential force, that is d within bracket dF1 equals to mu naught I1 dL1 cross I2 dL2 vector cross unit vector R21 upon 4 pi R21 square, that is the magnitude R21 square. So in this way we can determine a force on a current element I1 dL1 due to differential magnetic field dB2 by using a Biot-Savart's law. Now this is a small differential force on current element I1 dL1 due to differential magnetic field dB2. To get a total force due to magnetic force B2, we take a integration 2 times, that is a closed line integration L1 and closed line integration L2. Because here there is a two current elements I1 dL1 and I2 dL2, so we take a 2 closed line integration to get a total magnetic force. So the force on current element I1 dL1 due to magnetic field in second loop, that is B2, is given by F1 equals to mu naught I1 I2 upon 4 pi. This is a constant term, so we take outside the integration, into line integration, closed line integration L1, closed line integration L2. dl1 vector cross dl2 vector cross unit vector r21 upon r21 square. So in this way we can determine the force, magnetic force between two current elements. The magnetic force be attractive or repulsive, that depend upon the direction of the current. If the current is flowing in the same direction, there is a force of attraction, and when the current is flowing in opposite direction, there is a force of repulsion.